Okay, so today it's an exercise, at least a good portion of this will be an exercise. So what we do is I'll try and solve the assignments for you to get an idea of what elegance is, or at least to get an idea whether you got the solution right or wrong. And if we have time in the end, we will have our second date with Mathematica and with patterns. So let's see how far we get along into. Okay, assignment. 1DF15. Before getting into coding, I want to say two things. First, what you guys had to do very, very much resembles what you would do in real life if you were to come up with a program for your dissertation, for your doctoral studies, for your master's thesis, or for work. You would not start right away with a parallel implementation. You would not start right away with a C, C++, or Fortran implementation. What you would do, you would first try the algorithm with MATLAB. You would try to see if the formula actually spits out the right solution. You will check the accuracy. You will check maybe different approaches, and you will do all of that in MATLAB or maybe Mathematica or maybe Python, but certainly not in C. So what you guys had to do, it's very much like what you would have to do in the future. This is why it's important to come up with an elegant and smart code. You don't care about optimizations yet, but you care about the structure, and you want to be able to understand what is going on so that you maybe can convince someone else, oh look, I checked my algorithm and see it works fine. Or maybe you are testing different strategies, so you want to understand what the code does. Second point that I want to make is that when you look at an assignment like this, you say, oh, this is one of Bientinesi's assignments. So for sure, I don't need a computer right away, but I need a blackboard. So the first thing to do is to study what I'm asking, understand the math, and then the implementation should actually come easy and straightforward once you find the idea, the right idea. So that's what we do. We start with the board. We have to compute the FFT of an input vector. What is that? We just have to receive an input vector V. We have a definition for this matrix F, and we want to compute our Y. Did I call it Y? Yes. The trick is that our F is not a matrix, it's a product of matrices. It's going to be permutation. Let's call it Kronecker 1, Twiddle products, diagonal, and Kronecker. Okay, let's say Kronecker 2 and Kronecker 1. What are the requirements? You cannot work with these matrices directly. That's forbidden. So basically what I'm trying to tell you, and I said it I don't know how many times, I don't want you to build this matrix and then do matrix vector multiplications. That's not the way to go. Instead, we want to understand the structure of these matrices. So, obviously, since this is our input, we will start from the right, and we will traverse this expression from right to the left. So let's start looking at this K1, what it is, what it looks like. Now we need some sizes. Our vector V is of size M. So our Fourier transform is of size M. Okay. This guy here is composed of f of k and identity of m over k. we need some names. Let's call, so for our program, K becomes P. And then M over K, now this is annoying, so we say that M over K, we call it Q. So that our matrix is actually P times Q. Okay. Let's understand the structure of matrix K1. There are K, which means P, different blocks. I told you that f of K, f, any f is a symmetric, so this object here will have some number of blocks. How many blocks? P of them. P. Okay. This is our matrix f of K. Kronecker product with identity. It means that each entry of this block is the same. It's a block with all entries equal to each other. And what is the value of this entry? Well, this is the first entry of f of P. Then what is the second entry? Okay, that's the second entry of f of P. And so on. And all the entries over here are the same. Okay, that's not true already. It's not that all the entries are the same. The diagonals are the same, right? You're supposed to correct me. So, okay? Sounds better? Yeah? Now, if I want to multiply this matrix, that's what I want to do. I want to multiply this matrix times this vector. Well, this matrix is composed of 4 blocks. That means that my vectors will have to divide it into 4 pieces. So this length here should be the same as this block here. Then this length here, same as here, and so on. So if I have P blocks here, I need to have P blocks here. What is the width? Yeah?
Wouldn't it be more interesting to consider the whole thing with a stride? So for example, the first multiplication we do would be the first element of the vector times the first element of the first block plus the, what is it, q's plus 1 entry times the first entry of the second block.
If you want to do that, that's fine. It's no problem. I will go the other way around. So I was saying, so we will have P blocks. What is the size of each block? Well, this is easy. It's going to be exactly Q, because P times Q is the whole vector. So each one is Q, Q, and there are P of them. Okay, how many of you performed this kind of analysis? Okay, like 3 of you? Okay, 4 of you. That's good. Very good. So this is our starting point. Let's try to implement this. Why do I stop here? Well, because this is enough. I will not form the full matrix. I don't need that. I know exactly what is contained in each of these blocks. What is contained, I just have to look at FP. This is a small one, so it's fine. So I can perform my matrix vector multiplication. Let's try and do that. And then we go back to the math and we will progress towards left. So this is when I will make a gazillion mistakes, so you will have to help me. Edit my 1D FFT. Function, we have to spit out a vector. My 1D FFT. We take what do we take? A vector and okay, so that's a prototype. Okay, for sure we need some sizes. M equals length of V. So I take the easy case where M is already a multiple of P. If it wasn't, well, you have to do a little bit more, but for me this is enough. Q equals M over P. So now we know that M equals P times Q. Okay, we have that. Then, just to be sure, let's allocate our solution. Okay, so far so good. What do we need? For sure, we need the little matrix, the recursive f of p. So somewhere I need another function. Function spits out f, my f of p. What does it do? What does it do? Well, this is easy. You don't know how many times I make the same mistake, and for how many years. So maybe like this. Yeah, we like this.
Question.
Yes.
Will this result into the same as you gave us in the lecture? This e to the power of...
Sure. Yes, that's exactly the same thing. Okay, but then I should ask you. Why are you even asking me this question? You should be able to answer it yourself. FFT is a matrix vector multiplication. I am passing something. The what?
You're passing a matrix.
Yeah, which matrix?
The identity matrix is has a p.
So if I multiply a matrix times the identity, what do I get? The matrix itself. Okay, very good. Then I can say f of p equals my f of p. So I'm in good shape so far. I have gotten here, I have this matrix. That means that I implicitly know the content of each of these blocks. Now I only have to perform a matrix vector multiplication. Unfortunately, here the horror story starts because now there is a lot of indexing. How to do this? Well, we know that we will have p successive blocks. So for sure there's going to be a 4, 1, 2, p. No way out. We know this is going to happen. What? I am already thinking that I will multiply these blocks, this block times this part of the vector, this block times this part of the vector, and so on. That's what I am trying to do.
So we're effectively doing a sort of matrix multiplication. If you consider the right vector,
I am doing a matrix vector multiplication, absolutely.
you can consider the right vector to be a matrix in a sense. You have a lot of smaller blocks. You consider those vectors, then you have a vector of vectors, which would be a matrix. So there's no need for a 4 in the whole FFT.
Okay, you're going again at the other direction. What I'm doing right now, I want to show this multiplication. Okay? I see what you're saying. But we stick with this, okay?
So we can't only look at the whole Kronecker matrix and write K and vector V computation if we look the raw K1 matrix and not.
I didn't understand that. So what are you trying to say?
Why we derive the classical matrix K1
Yes?
matrices NP because when we cannot
I am dividing into.
yeah, but what we cannot compute quantum matrix
Absolutely, yes.
and only have a matrix
Hmm.
multiplication with vector multiplication.
Yes, that's what I want to do. I want to multiply this matrix times a vector, this matrix times a vector, and so on.
Yeah, but if we can compute K1 times and the whole vector V.
You cannot compute K1. That's forbidden. You're not allowed to compute K1 altogether. That's a big matrix. No. We don't have. We don't want to do that. We can only operate on smaller matrices. So let me see if I can do this. For now, I set up a loop so that I can march through these blocks. And then I have to generate something. That's going to be the y vector. So I will generate something here equal this row of blocks times this column. Okay. So that's going to be y plus fp of, let's say, ij. What is fp of ij? It's the entry that identifies each block. So I know already that I will need an I array as well. So to make it sure, I can even use the dot star or star. Doesn't make any difference here because it's just a scalar. And what do I multiply? So the fp, I am accessing the block, and now I have to access part of the input vector, so v. Okay, this is the operation that I want to perform. I want to do it. You see that there is an I index already. I want to do it for each row, so I need another loop. Okay, and at this point I have to do some index operations. Oh, first of all, why is E from 1 to P? Because this matrix is a square, so it has as many column rows as block rows, so it's P by P blocks. Let's work on this index. Okay, this is the output, will be it will be this object here, then this object, and this object, and so on. So since I am afraid of messing up with the indices, and since the indices are the most crucial part of this program, I better do the following. Let's forget about computation for 1 second. Let's make sure that I get the indices right. So what I want to do, I want to compute the indices for my output, for my y. At the first iteration, I am tempted to say that I have to do this, maybe this, from 1 to q. So I want to identify the indices of this first block. How many entries does one block have? We said it already, q. So the first set of indices is from 1 to q. Okay. The second set of indices will go from q plus 1 to 2 times q, and so on. So now we write a smart formula that does this, something like maybe, let's see, q times I minus 1 plus 1 So, not there. Here. Okay. When I is 1, this would be 0, but in MATLAB we start from 1, so that's it, up to q times I. Q times I. And hopefully these indices are fine. So now I will execute my, now I don't know what I'm doing. Here. Oh, I'm doing Emacs. Save it, please. Yeah. All right, I will just execute my program. 1D FFT. Let's say random 12 1 3. Okay, so what do I get? First of all, I have way too many indices. Yeah. I don't need this yet. Okay, so I'm asking my program to compute the FFT of a vector of size 12 with p equal 3. P equal 3 means that each block will have q. We know that q is 12 divided by 3, so it will have 4 indices. So it sounds like I'm doing the right thing. I'm identifying the indices of y, then next step, and then next step. So I'm identifying the right indices for my output. Maybe to be consistent with what I've shown there on the board, I should have p equals 4. So I will have 4 pieces, each one consisting of 3 entries. Okay, so it looks like I got the indices right. Since the indices are the nemesis of this program, I will use some trick. How about I call this thing as index j? No, index y. Okay. Now I know that my y of index y equals itself, okay, plus this is the block in which we are. And now I have to identify the corresponding entry of V. So as I am traversing the matrix from left to right, I need to identify the right block in V. So I need more indexing.
Small question.
Yes?
Is it really necessary to have this addition y plus fp and so on? Does this y is really necessary? Because y is at the beginning zeros, so we're adding zeros.
No. That's absolutely necessary.
That's okay. That's okay.
Okay. Did everybody get that? Yeah, okay. So, this thing depends only on I, so we put it there. Now we do something similar for V. Now you have a J and J. In case you think I'm cheating, we can do the same story. I comment this out, and we look at our index V, but we will get the exact same indices. So I would rather skip this step. Okay. Is everything correct? No, here something is missing. Index V. Anybody objects? So far, so good. Okay, so here is the here is the important message of this lecture. Okay, this is what the computer is, what the algorithm is supposed to be doing. Whenever you implement this, you always have to keep in mind, how do I test what I'm doing? So this is what I am attempting to compute. I always need to find a different way of making sure of testing whether my solution, my y, is actually doing the right thing. So for testing purposes, now it's perfectly fine to compute the big K and to perform K1 times V, just for testing purposes, so that we can raise the level of confidence of what we have done. So I'm going to do it right away. Now I have to compute my K1. K1 is a Kronecker product of f of p, which we have, times I of q. Is that correct? I think so. And if I am lucky, actually I don't need this. Well, that's okay. Now if I am lucky, my y minus k1 times v should be small. That's small enough. But is that enough to say that my program is correct? No. Let's keep trying. Okay, now my level of confidence is pretty high. And it looks like I'm really doing the right thing. So now we comment the nasty, the ugly part.
So just one thing.
Yes.
So here the size of vector is 12, and you take p equal to 4.
Yes.
So in the slides you said that it should be less than equal to square root of m.
Yes, because I made it to help you guys. Square root of 4 of 12. So if I take 4, it's no different than taking 3. Because 4 times 3 is, so I just did it for you guys.
So it's not a rule sort of.
No, it's not a rule. It was just to simplify your life. It doesn't make any difference. You can go all the way. But 12 is the same as 1 times 12, 12 times 1. Actually, the implementation is not the same. The computation is not the same. But I just wanted to. Did I say it for? Oh yeah, I said it for 1 DFFT. This makes more sense for 2 DFFT. But yeah, the computation is not going to change. Now back to the math. We know that we did K1 times V accurately, exactly. So we did the right thing. Now we have to push D into the picture. Yes?
Actually, I really would like to present my solution of K, because I have a totally different approach.
Yeah. Let's finish and then we look at alternatives. I like to look at the different solutions. In fact, this is just one of many. But yeah, let's do it once I'm done with the whole thing. Now we want D. Okay, that's what I was doing. D, in fact, D, we don't need to look at it on the board. We just look at my slides. I define D over here. So D is a diagonal matrix. It's composed of many diagonal matrices. But in fact, there is only one diagonal matrix that defines the full D. It's this smaller D. So why don't we define this object here, and then everything else can be expressed in terms of that. So that's what I'm going to do with my D. D equals my D. Okay, now the size. This is important. We have to get it right. D is defined in terms of M, and M is the full size. And in terms of this J, and J varies from 0 to, I think this is Q. So we want M and Q. And then what do we have? x minus 2 pi. That's I. Haha. No.
You can use one I, so it's always the imaginary unit.
Which one?
One I. You just write one I and it's always the imaginary unit.
That?
Yeah.
Or
Thank you.
just use -2i.
Minus 2i, like this?
Yeah.
Thank you. Okay. Here I have to multiply times all of these guys. Well, why don't I just do it like this? Q minus 1. I am paranoid about precedence, so I'm going to do this. Okay.
You're not going to be happy. The
Possibly.
Parentheses could probably start before the 0. Like that. No, you have a lot times 0, 2q minus 1 as the only term.
No, I think this has precedence. I like to live a risky life. So let's try this. My d of q. Let's see what I get. That's not what I wanted. Oh, yeah. This is what I wanted.
E to the 0.
That's what I wanted. I don't know, maybe. So, how to figure out if this is correct? I guess one could plug in the numbers, or we just trust it. Okay. So, yeah, this is fine. Let's go back here. We comment this. Now, yeah.
This my d is just the small d you are using and not diagonal matrix form.
I am showing what it is. So let's look at what D looks like.
It would be an easier life if you had a distinction between big D and small d.
Okay, makes sense. I like your comment. And D is this object here. Now let's look at what happens when we multiply a diagonal matrix, a block diagonal matrix from left to the right. Continuing our 4x4 example, I can delete f of p, and I can put a 4x4 diagonal matrix. If you have done some math on your paper, you see that this diagonal here multiplies all the blocks of the first row. This is the second diagonal, multiplies all the blocks of the second row, and so on. Can anyone, yes?
I have a question about Q, because Q determines the dimension of the matrix.
Mm-hmm.
Why can we assure that Q is never rational or irrational?
Yeah, you're not sure. That's an assumption. I'm cheating because I'm the professor. I can cheat. If you're a student, you cannot cheat. So if this doesn't hold, you have to pad, and then it will hold. That was the first line of the assignment. Yeah?
I'm pretty sure that what you got as the answer is not what you want to get if you try it. So please verify D. Instead of just saying we should skip it.
We will.
Because if I verify your D, I get a wrong result.
Okay, I trust you. It's very possible. That's why I say that you guys should help me. Notice that I have already made another mistake. Nobody noticed. I said that when I multiply a matrix D, I will multiply all of these entries, all of these blocks. But we don't have these blocks anymore because this has been multiplied times a vector. So all of these actually now is just a vector. And now, this first diagonal will multiply the first block, the second diagonal will multiply the second block, and so on. Okay, I like that somebody interrupts me. Go ahead.
You have
Mhm.
you could simplify it via just adding it.
Yes, precisely. I could, instead of defining this matrix and doing a matrix vector multiplication, I could take the first entry, multiply times the first entry of the vector, second entry, multiply times the second entry, and so on. Absolutely. Some other comments?
There's an operator for that.
Sorry?
There's an operator for that.
Yeah, there is.
You really
There is an operator. Our diagonal is just a vector, so we will have an operator for that. Some other comments? Yeah?
So as a matter of fact, it will turn out that only the bottom right part of D has some exponential elements and everything else has ones. So that's the only part which we actually need to multiply.
I wouldn't be so categorical, but what you're saying is correct, as in this matrix here is the identity matrix. So I don't really need to multiply this object times that. But all the other diagonals, yes, I do have to perform that.
Well, actually, the first element of the second matrix as well as well.
Yes. Okay. Okay, so let's do this. Okay, it looks like my diagonal is not correct. Probably it's because of the 2i. It's easy to blame it on the students.
It's very
So-
easy, but it won't help you fix it.
So why wouldn't it work? Why wouldn't it work? Let's do the math one by one. You guys seem to be sure that it doesn't work.
Well, if you do x of 1, I get something with an imaginary part. I don't see any imaginary part in your answer at all.
Probably it's because it's the 2i. I'm not kidding. No, okay. Sorry, I doubted. So,
Well, it's because the column does not take precedence.
okay, then I will put some parentheses and our life will be beautiful. Yeah, of course, this is not there.
I think we can see anything.
0, we can do?
We can see anything.
Oh. Hmm? And q in this case is q is 3. Q is 3. 4. P is no. If P is 4, Q is 3. Okay. I am pretty sure. Yes. Looks better, huh? So, I don't know if I want actually. No, that's a bad idea. Maybe this. Okay. So now we have our diagonal. Are you happier with this diagonal?
Yeah.
Much happier? Okay. So let's compute, let's assign it. Let's say d equals my d da da. And now, yes, there are all sorts of possible optimizations. I agree with you guys. I will go brute force with a for loop to q. Okay, why? Pa, pa, pa. The I is the same story, okay. Y equal D. So yes, times okay, the indexing as usual is nasty. Let's see what I'm doing. Here I'm simply extracting the portions of the vector y. Well, in this case it would be here. And it's the same because I'm multiplying times a square matrix. So I'm marching again in the same blocks as before. Now the question is, are the blocks of D, do they have the same size as the blocks of K? And the answer is yes. So the blocks of K, they have the size Q. I see, I'll take the question in 1 minute. And the blocks of D, this thing we decided that it's also Q, so they have the same size. So I'm good. So this is good. And then I'm skipping the first block, so that's why I'm starting from 2. So I'm skipping the first diagonal block. I am here when I equals 2, but my exponent for that should be 1, so I shift everything. I subtract 1, I shift everything, and then I multiply times the corresponding block on the right hand side. And I think this will work. You don't think so?
I think we should consider element-wise multiplication.
Element-wise multiplication. That sounds like a good idea. Wait. Yes, that sounds like a good idea. Or I put a diagonal in front of this thing and I form a matrix out of that. Either one. Let's see how we're doing. So back to what I told you before, we have done this, now we have to find a way of testing. So we always have to do something and come up with a way of verifying the result. Now I will call Z times V. Okay, so Z is the exact solution up to here, and now I have to do D times Z. Unfortunately, this is nasty because I have to form the big D, which I really didn't want to do, but I guess I have to. So how do we do that? We just need a vector, and then I will put vectors. I will put copies of D over this vector. So we have another for loop. Let's go. Yeah? Sorry?
You could use Kronecker function. You could make up as the identity matrix
Yeah?
and Kronecker multiply it with D times K.
I don't think so, because these are, times, what is K?
Well, variables are not read.
So I have two comments. If you're suggesting to use a Kronecker product with what we just computed, that's not a good idea because I have to test that. If you're suggesting to use the Kronecker product to generate these, that's not possible because these are powers.
Yes, that's why. That's why I say identity matrix with the size of how many elements of D, small d we have. How many small d we have? K, we have
Q.
Q.
Oh, how many small d's? We have a P of.
Small d, so we have an identity matrix of P.
Yeah?
And this Kronecker
Mm-hmm.
D, which has the size of Q,
You're saying Kronecker I of P.
and then diag of D to the power of
That's not going to work. The power of.
K.
Mm. What were you going to say?
We can use the exponentiation function to compute a matrix over I and j, because if you just consider basic exponentiation rules, if you have an e to the something, you can just multiply together.
Mm-hmm.
And
Yeah,
you
yeah, yeah.
just put a vector in
I see,
the
I
x
see, I
and
see.
put a matrix.
Yeah, yeah, it makes sense. I agree, but
actually, based on again that observation, I will again say you just need the bottom right of T.
This is for
that is not, yeah, that is not true in the most general case.
So we can
So yeah, you are perfectly right, but I want something simple for now, so let me try to attach all these copies of D with different powers. So how do we do that? Let's say big D of equals
we have to do something different than what we did before, because otherwise we're just testing the same bugs.
That's right. Now I'm creating a full D.
But you're doing it with the three parts that you already used and want to test with that.
No. These we tested by hand. We know that it works, this D, and the rest, it's different, right? Now I'm creating a big D.
This huge heavy xy, which you said was a problem in this program.
This is a test, remember? This is not part of the computation. So, and now what do we have to compare? Z, I have to do big D times Z with my Y. Okay. Phew. You guys are making it hard on me.
Big D is
You should remove the semicolon.
Big D is what?
Big D is not pre-allocated, and now it results in a vector. So big D will be a vector.
Big D, yeah, that's a very, very good point. Very good point. So, yeah, I didn't allocate big D, but in MATLAB I can do that. Other big D didn't work. Big D didn't work. Why didn't it work?
Because you might consider going I to the p if you do q indexing on the inner side.
I to the
You're doing a loop
P?
over 1 to q, and you're indexing with q times your index. So you're going to q squared until p times q.
Yes, that is true. So we said that we have p blocks of q size.
By the way, it's the same in the function above.
It's a what?
You're doing the same in line 21 and 22.
21 and 22. Good. Okay. That's a collective effort, and it seems to be working. Okay, very good. Let's move on. So now we can comment this out again. Now comes the easy part. So we're done with this. We're done with this, and what do we have? We have a vector. So now we want k2 times a vector. What is the structure of k2? It's here. It's the identity times some Fourier function, Fourier matrix. So, since it's the identity, we know that we will have entries only on the diagonal. And what is going to be in each of these blocks? Well, that's a Kronecker, the right matrix, so it's going to be Fourier, 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 Fourier. We said already what happens when we multiply from the left. So the diagonal matrix from the left, this f only works on this, the second f only works on this, and so on. What is this operation? Recursive call to a smaller FFT. That's very easy. Let's just make sure that the sizes are the same as before. We need to see how many f's are here and how big each f is. Okay, I of k, it determines how many blocks. It's I of k, so it means there are k. K is p. Okay, so once again, we have the same structure. We have p blocks, each one of size q. Let's perform the multiplication. This is easy. We can just take the same loop. Now we start from 1. And then we say that this thing is FFT of itself. Okay? Yeah. Now we have to go back and check, but this time is easy. This time is easy because we can just form my K2. How did I call it before? Oh, I didn't call it. I just did it. Okay, Kronecker of i's of P FFT I of Q. No, come on. Ah, okay. That's what you're trying to say. Yes, thank you. And we multiply times our z. After that, we say, maybe we assign it, norm of y minus z. This should be easy. Yes. Keeps working. All right, and now we only have the final step. The final step is the permutation matrix. Nobody should ever think about creating a permutation matrix and using it to multiply. Permutation matrix, it's just a shuffling, so don't ever think about creating a permutation matrix. Same as don't ever think about creating a diagonal matrix. Never ever should you do that. Now we have to see how this permutation works. And I created all sorts of fancy pictures. You should thank me for that. I even noticed that I put, no way. Yes, there is a typo, but I was nice and I went online and I created, this is me translating, by the way. Oh man. How bad is this? So, and I fixed it. Here. Anywhere? Okay. So there was a typo, nobody noticed. So I fixed this. Now, as I said, this is not a matrix, this P, it's just a reordering matter. So we have to find a way of shuffling the indices around to implement what I displayed. Yeah? And that's exactly what I'm going to do. So we start from our indices. Matrix is of size 12, so we will have 12 indices. Okay. Then we can reshape the vector. If you don't know what reshape is, it doesn't matter. The idea would be to arrange this vector. So right now we have 1, 2, 3, a long list of numbers, and the idea is to do something like this: 4, 5, 6, 7, 8, 9. Okay. I came up with this last night, by the way, or maybe this morning.
You can do that along arbitrary dimensions. You can assert dimensions.
And then you read this thing by rows. So if you read it by columns, you get the input. If you read it by rows, you do 1, 4, 7, 10, 2, 5, and so on. So how to do that? If you know reshape, you use reshape. Otherwise, it's a matter of building this small matrix, each column being part of that input vector. Fortunately, I know the command reshape, so I'm lucky. That's what happens. Now, I don't know which one is 4 and which one is 3. I have to work on the indices, but this is the idea. I take this vector, I put it in this form, then I transpose it and I read it back. And you guys know how to do it because I showed you. We just do W like that.
It's dangerous.
And then, oh, I'm sure it's dangerous.
Now you should consider doing a
Here we go.
complex transpose.
I agree with him.
This is syndexes.
These are indices, guys. Don't be paranoid. calm down.
On the indices, if you can just use the vector.
Calm down. Okay, so what do we have to do? We could write a function that does this, or we could perform it directly on the vector. I think I'm okay writing a function so that I can figure out if the indices are fine. Function P is not a matrix, it will be a vector, of course. My P. I don't know which one I need, I will have to try. Ta-ta. Oh, this P is bad. Pair. Okay, so what do I do? No, what is it? Reshape. Reshape.
There is no P in this function yet.
Notice how terrible this is. I'm using the same variable for a matrix and then for a vector. Absolutely terrible, but hey, MATLAB lets me do it. So I'll do it. At this point, I'm not even sure if this should be Q or P. I'm just guessing. So we should probably test. My P of M comma P. Let's just try. Okay, what do I see? I see that I get blocks of size 4. I'm not happy about that. So clearly here I need a Q. It's even worse than before. So.
Your block was size 3?
Why it is worse?
Oh no, okay, yes. Okay, so then what do I have to do? I have to say that y of these guys equals y. And if I'm lucky, I got the right answer. At this point, I can simply test with FFT of, I can forget about everything else. I can just say FFT of v minus my y. Okay, if it works, it's gonna be a miracle, but no, y. Yes! Thank you, thank you. And here we have assignment number 1. We remove all the test routines. Did I remove them already?
V equals from
line 30.
Okay, thank you. This is not here. Then the big D we can kill.
32, 31.
No, well, this we leave. No, okay, that's fine. Okay, solution. Fits one page, and it took as a collective effort 1 hour. By myself, I would have done it probably in 30 minutes, but okay. So this was the assignment, part 1. And I agree with you, the diagonal part, which is here, could be better. Do you wanted to come over, please?
So the complexity of this algorithm, take into account what is written here, not the theoretical complexity, is a bit more than n log n.
Yeah, in order to go to n log n, you would have to recurse down. You cannot stop the recursion at this point. You have to go down. Yeah. Chalk, there is plenty. I can offer you a board. Should I kill the video?
Yes, please.
Go ahead.
The thing, I just have another idea for the calculation, the first calculation, the K1 matrix, which was Fp from I n over P. Yes, this is the matrix. We want to multiply this as our input vector. And let's just say it's I assign it to y. Now, the special feature property I'm going to use about Kronecker is that this is actually equivalent to a matrix multiplication. This means it's a reshaped, it's y vector in the form of matrix with this dimension. It's just reshaping. And this is input vector reshaped times Fp transposed. Doing it this way, actually, why I search for this? Because we have here Fp, and it's something like, hey, we can use FFT in MATLAB. So how can I make it that I can use FFT for this function? I have to have a form like that. I can FFT of a vector is something like Fp times vector. So I need this kind of representation.
Yeah.
So I can just
Transpose everything.
transpose everything. And this way, I can now use FFT of this. Calculating it, transposing it back, reshaping it, and then the new.
That's good. Do you know why that is the case?
I saw a lot of paper, at least 2 papers using this.
It's
And-
actually quite simple. You just consider when you reshape that, you order all the blocks next to each other. When you transpose them, you have a vector that you want to do, a column vector you want to do FFT of, then another column vector you want to do FFT of, and you're not just walking the whole K matrix block by block or line by line, but you're essentially walking the F
Block by block.
and then you're applying it to each column vector of what you're doing.
Yeah, okay, this is good.
And if you go on from that, you can compute the whole FFT in about 2 lines with 2 reshapes, 2 FFTs, and a couple of multiplications.
Let's move on to number 2. So, exercise number 2. Having done number 1, we don't have to actually write the code, but I'm sure that all of you recognize that this is the assignment number 1, homework number 1. And I had already told you how to solve assignment number 1 in an elegant way, so where did you steal it? Oh, it's here. So I imagine that you all replicated the winning solution from last week, from last challenge, since the computation was exactly the same. Okay. So here we have identity, identity, identity minus identity. Since I have these 2 column blocks, I have to split my matrix into a block of rows. And since my right matrix is partitioned also in 2 by 2, then I will have to partition over here to have a multiplication. So this is identity, identity, identity minus identity. You don't start coding before you actually do some math. You do the math, and what you find that this is our matrix C from assignment homework number 1. And here is a C top left, a C top right, blah blah blah. If you wonder what that is A top left plus A top right. A top left minus A top right. And this is B top left, B top right, B bottom left, B bottom right, and so on. And then our C top left will be B top left plus B bottom left. So now I have to add these guys together. Our C top left is B top left minus B bottom left, and so on. Okay, and I showed you already how is a nice way in MATLAB to do this. You start off, you say A top left equals our matrix X of blah blah. A top right equals blah blah. Then something here, something here. Then you have B top left equals A top left, A top right. And right next to it, B top right equals OK. And then you have a C top left, OK, 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 OK. So,
but we shouldn't use matrix of size n times n, so we can't use B top left. It's like cheating because we.
what do you mean?
Because we don't use a matrix, we allocate enough memory for. If you use it, 4 variables of this size.
This is a small one.
Yeah, but we have 4 of them.
Well, too bad. I told you, I specifically said, come on guys, be flexible. You know that your input matrix is...
You can use 10 for a variable and do it.
yeah, okay, but come on. I specifically said it because I felt like, come on guys, be flexible. Your input matrix is n squared by n squared. As long as you don't generate more of those. Now, we are done with this first step. And now we have to do diagonal and diagonal. And again, don't be tempted to just use the diagonal that you used in part 1. Let's be a little bit smarter than that. How can we be a little bit smarter? So we have our 2 by 2 matrix. Let's call it, what do we want to call it? X top left, or maybe C, since we know C, we know very well what it is. And now we have our 2 by 2 diagonal matrix, which is D0 and D left to the 0 and D left to the 1. And over here we have D right. I don't like small letters for matrices. D. And D right. Okay. But for sure you know that this is the identity. And this is the identity. So, okay. So what do we get? Maybe I should turn off the... This object multiplies the rows, so doesn't do anything. And this object multiplies these two. So this object works on the columns. The identity doesn't do anything. This only acts on the right column. So over here I have D right 1, D right 1. So our C top left, no operation. Our C top right, one right multiplication with the diagonal. You can speed this up if you want. You can be smart, or you can just leave it as it is. Bottom left, one diagonal product on the left, and the only bottom right gets 2 multiplications. Okay. And we are down to now Kronecker product on the left and Kronecker product on the right. Let's see what that is. We have, let's call this matrix, let's call it, I don't know, Y, no, not Y, Y it's the output, C bar. And we have I2 F whatever, M over 2, C bar, it was an M, of course. Yeah, it was M. And here it's N over 2. So we have seen already in the first assignment that this is Fm over 2, Fm over 2. Once again, diagonal block matrix, Fn over 2, Fn over 2. Why don't we multiply everything out? And same story in every block. Okay, and similarly here and here. And this is
FFT2.
precisely, it's a recursive call. It's FFT2 of my top left block, FFT, two-dimensional FFT of the right block, and so on. So you can even do either your code recursively, or FFT, or MATLAB's FFT of C top left, and then FFT 2 of C top right, and so on. Okay, recursive call was done. Then down to the permutation, and well, fine. The permutation, you understood what the permutation was like from part 1, so now it's a matter of reshuffling. In part 1, I reshuffled over here a vector. So I applied the permutation on the entries, let's say on the rows. If you have a matrix, you apply the permutation on the rows, comma, permutation on the columns. So that's the only difference. Part 2 was that easy, yes. Questions? Somebody has a look like we have a dad in the... Was it really so difficult? No. Yes.
I would have a question,
Mm-hmm.
but actually I tried to make it in general, not for p equals 2, but for...
Okay, that is considerably more difficult.
Okay.
That's a different story. That's why I fixed it to 2. Again, I wanted to be nice with you guys. And
The name of this algorithm?
this is just recursive. So normally the FFT algorithms, they always use they call it dimensionless algorithms, which means they always go down to dimension 1, and they do tricks like what he presented. And this is a dimension preserving algorithm. So you don't change the dimension. If you are in 3D, you keep working on three-dimensional objects down to three-dimensional smaller FFTs. Here we got down to two-dimensional FFTs. So we'd never go to one-dimensional or so. So that would be a dimension preserving algorithm. All right, so that was part 2, and that was supposed to be very easy. I hope it was for you guys. Not so easy. Part 3, I don't know if it's worth going into. I like that somebody did the following. In addition to testing with all of this procedure, I think that pretty much everybody, the assignments that I saw until yesterday, everybody did it right. Maybe somebody didn't look at the second argument of this IM show, and so the image looked much worse than it could. The second argument, I think it's the maximum value or something. But somebody did the following, really interesting. So not only did they let's say, compress the image, they actually saved it, and they looked at the size of the file. And it turns out that even though you can eliminate 50% or more of the frequencies, the file is not 50% of the original size. And that is because of how the JPEG is stored. But if you knew that your image actually only has the zeros on the border, then of course you could devise a compression scheme that beats JPEG by a lot. So the images that I gave you maybe were not the best ones to see this phenomenon, the ripples, those waves close to the edges. Next time I assign this, I will make sure that I give a picture with lots of sharp edges, lines, and corners. And as you decrease this k value, you see that next to these lines, some artifacts start start popping up. And so, yes, of course, you get to a point where everything is blurred. But these artifacts, these wobbles, they are the first thing that tell you that some high frequencies are being dropped. So they appear much earlier on than when you lose definition in the image. Okay, I think that everybody, or at least all of those assignments that I looked at, they were doing the right thing. So, questions? We could have a 5-minute quick date with Mathematica and the patterns, but maybe it's better to just postpone it to next Tuesday. So I'll see you on Tuesday.